Hi listeners, today's lecture is on Introduction to Computer Organization and Architecture. This is coming under the paper of Digital Computer Architecture. Let's start from the beginning. We are starting with the concept of how a simple high level program will be executed in the computer system. Let me take an example of a C program snippet where within the main program we are declaring three variables A, B, C, and from the user we are getting two values for A and B. Thereafter we are simply adding them up and storing the result at C variable, and this particular result will be displayed within the console using printf C statement. So this is a simplest program by which we are taking some values through keyboard. This is an interface to the computer system, and we are producing the output to the console. That means using the VDU we are providing the output to the user. Now the basic question is how this program being executed is within the CPU, whether it is automatic or some logic is basically built up in the hardware level, how this program is being executed on the CPU. With this question, how it is relevant to the paper computer system architecture, we come to know one after another. This is the program snippet what I displayed in the first slide. This is written in C language, and as if with our programming concept we come to know that C is a high level programming language, and this language is being used to write programs to solve certain general level problems like mathematical problems or general purpose problem situation. Now if we take this snippet, this scenario, now this high level programming language is being translated using several intermediate translators. These language translators we come to know from our basics that compiler. That means this compiler actually translates this high level programming language into assembly language, and this assembly language now being translated by the assembler, and assembler will get the assembly language code, and that will be essentially translated to the binary codes, and underlying operating system having the responsibility to take this assembly language code into binary codes, and binary codes to execute that program by the CPU and to produce the results. Here we are observing there are 6 levels of programming languages, starting from the high level programming language to the digital level logic, that is how the program being executed using the digital logic circuits. Obviously there is a dependency in between top to the bottom, that is it will be translated first by the compiler, then translated by the assembler, then assembler to linker, and by linking the total code that will be provided to the operating system, and thereafter OS will execute that program through its microarchitectural level, and from that level digital logic circuits will execute that particular program. Now, if we look at this C program, uh, the first thing it is coming as input A. That means we are we are getting an input through the keyboard, and port A is designated for the keyboard. Basically, through keyboard, the in instruction will instruct the CPU that we are getting an input through the user interface. Now, the second step is uh, that particular collected value, which is essentially collected by the port A and stored at buffer level, that will be stored within the memory location A. Okay. So, from accumulator to memory location A, that particular value is being stored. Okay. Now, again the same instruction is used to uh, take another value for B using the keyboard. So, essential instruction is input A, and the accumulator is storing the value which is provided by the user, and that value is being stored at variable B. So, the fourth instruction coming as store B, that is from accumulator to memory location B, the value is being stored. Now, if we remember the C program snippet, thereafter we immediately perform the values of A and B that will be summed up. So, in the fifth statement, memory location of A is added with memory location B, and that value is being stored at accumulator register, and from accumulator register, according to the C program snippet, C equals to A plus B we have mentioned so far. So, that result will be stored at variable C. Now, just storing the value of C is not enough for our requirement. Now, it is the time to display that value of C to the output device. Now, the next instruction is output B. That means port B is designated for the output device attached to the system, and out is the essential instruction for that purpose. And the last statement is halt. Halt means if we look at the C program snippet, the last curly braces is actually used for end of the main function, and that essentially end of the program, and that is why this instruction halt is used to indicate this is the end of our program execution. So, ultimately what we come to know that the simple C snippet is now being translated into corresponding assembly level language, and in this assembly language we get 8 such instructions, and that instructions is being now generated by the compiler. Now, this assembly code is now be translated to its corresponding binary language or say machine level language. So assembly level language is an equivalent binary code is there, and there is an one-to-one correspondence between the instruction being generated by the compiler and the binary code which we are expecting to execute in the system. And as if we know that binary code is being stored within the computer system with an extension of .bin file extension. Okay, and after getting the binary file, the linker of the C compiler, C compiling environment, linker is actually links all other pre-compiled files which are associated to our C program, and that program is now being created as an executable file with .exe file extension. After translation of the previous assembly level language code, we are getting such binary codes, and this particular page is actually displaying a simple code translation, and we are assuming that uh, we are essentially translate this in all the instructions using 8-bit binary code. 8-bit binary code is used for instruction, and 3-bit code is used for operand specification. Input A, this instruction is now be written with 4 nodes 1001, where the second 3 bits 001 is actually designates port A. So the first 8 bits is actually designating the instruction, and 001 is used as the operand to that instruction, which is nothing but port A here, and port A is designated by 001. So this is the assignment we are assuming just. This is not the actual one, and the real fact is actually if we look at the every microprocessor's data file, how they can represent the instructions, from that thing we can get the realization, actual realization of the representation of every instruction. Similarly, in the second instruction, we are storing the collected value from accumulator A to memory location A. That means we are storing the value of accumulator register to the memory location A. So store this instruction is now be represented as 4 nodes 1100, and memory location A is represented as 100. So these are fairly simple assumption, not the real one, again I am saying. So with these assumptions, we are translating the assembly level language code into corresponding binary code. So from that we come to know that what the instruction is, what the operand is, and these are the basic ideas we can come out from the discussion. Now, while we are going to execute such executable code with our system, now how it is being executed? With that question which is raised in the first slide, to come to the answer, in 1945, John von Neumann proposed an architectural model which is popularly known as stored program architecture, or sometimes it is known as instruction set architecture. With that concept, it is stated that every program, while it is going to be executed on the CPU, the instruction and data will be stored into the main memory, and from main memory it will be executed by the CPU one after another by some control circuitry. And as if we are observing in the picture in the right side, it is displaying that there will be a processor, and that processor is actually interfacing with the memory, which is basically called as main memory, and any other devices attached to this computing system is designated as the input or output devices. That means this simple architecture is saying that while we are going to execute certain program, that program must be stored within the main memory, and from main memory the processor will take the instructions one after another and will execute within the processor. But there is a problem which is popularly known as von Neumann bottleneck. This bottleneck is being alleviated by the then proposed Harvard architecture, where memory there is a splitting of memory devices. One portion of the memory is used to hold the instructions only, and another part of the main memory is used to store the data. So even if there is a dedicated main memory, but there are certain subparts are there where instruction memory and data memory, these two memory portions are segregated. So whenever an instruction is going to be executed by the CPU, its corresponding data will be available from the data memory. This will alleviate the von Neumann's bottleneck, that is the with respect to speed mismatch or data access to the CPU is coming faster than that of the von Neumann architecture. But these two contemporary architectural model is still be in use in today's computer as well, where every program which are going to be executed by the CPU, that must be bring into the main memory first, and from main memory it will be executed one after another. So with that concept, in today's machines are also being developed and being used in reality. So with this concept, this simple architectural model is being displayed in this picture, where the CPU is there. Within the CPU there are three basic portions. The first one is known as ALU, that means arithmetic and logic unit. The second portion is control unit, which controls the execution of every instruction, and there is an interface between main memory as well as input output devices. So these all the devices being attached to the computer system is being displayed with the help of arrow-headed lines. The data paths are also displaying how the data being transmitted from one component to another. The essential components within the ALU are AC, AC means accumulator, MQ, the memory quotient register, DR is the data register, IBR the instruction buffer register, IR instruction register, MAR memory address register, PC is the program counter, and the control circuits generates the control signals which are to be used to synchronize all the digital elements as well as the instructions that to be executed by the ALU also. So all these components are being gathered to make the ISA model the simplest model for how to execute a C program or any other high level programming language is being executed by the CPU. So with that ISA model, this lecture being concluded. Thank you for watching, and we'll start from the next within the next lecture we'll go for the how to execute the C program in the next video. Thank you all.